So hello and welcome back to this lecture. In this particular lecture, we will talk about the Hessian matrix approach to find the maximum or minimum value and the points of maxima and minima, which are the points of extrema of a multivariable function. Okay, in multivariable, we here in this particular video will be taking the simplest multivariable function, which is of two variables. Alright, so let our function z be x square plus y square. So this is our multivariable function. Now you already know, we have discussed in the previous video, to get maxima or minima, the first step in multivariable calculus is also to compute the critical point. And how do you get the critical point? For the critical point, you have to equate the gradient to 0. Okay, let's find the gradient. So recall what a gradient is. Gradient is denoted by delta f, delta f, and gradient basically is a vector which contains all partial derivatives of the function as its components. So the partial derivative of this function will be del z by del x with respect to x and del z by del y with respect to y, and that will be my gradient. So let's compute these partial derivatives here in the side, and then we can equate them to 0. So del f by del x is differentiate with respect to x, del z by del f. Okay, let's call this f. Okay, that will be better. Okay, so let's differentiate with respect to x. So we'll take y constant. So this will be derivative of x square plus derivative of y square with respect to x. This is a constant because we are differentiating with respect to x. So this is 0, and derivative of x with respect to x square with respect to x is just 2x. So this is 2x. Similarly, del f by del y, your y, it will differentiate with respect to y. So your x will be a constant now, and that means this derivative will be 0 plus derivative of y square, which is 2y. So what is my gradient going to be? My gradient hence becomes 2x comma 2y. Okay, now let me use this point, equate my gradient to 0. So the critical points of this function will be 2x is equal to 0 and 2y is equal to 0. We have to solve these equations, and you know the only possible solution of this particular equation system is 0 comma 0, because this means x is 0, this means y is 0, and only way 0 comma 0 can be achieved is when x is 0 and y is 0. So 0 comma 0 is the only critical point of f. So this is our first part of the solution. Alright, now what we have to do is we have to get the Hessian matrix. So this was the first step. The second step is get the Hessian matrix. Now recall, we have discussed it before in our theory lecture, that Hessian matrix is a collection of all the partial derivatives, the matrix which collects all partial derivatives. So h of f will be del f by del x squared. Okay, these are higher order partials. Del 2f by del x2. Then you have a mixed partial del f by del x del y. Then you have another mixed partial del f by del y del x, and then you have del f square by del y2. Okay, sorry, the notation is a little wrong here. Okay, this is a matrix of second order partial derivative. Just like you take second order derivatives, you have second order partial derivatives, and a collection of these as a matrix is a Hessian matrix. Okay, this we have already discussed. So if you have a doubt here, go back to the theory lecture and watch it. Now this is our Hessian matrix. So what is a Hessian matrix? Hessian matrix is this collection of partial derivatives. Now what we have to do is we have to get the Hessian matrix for this function. We have to take our given function and we have to compute the Hessian matrix for this particular function. Okay, at the critical point. So this Hessian matrix will now be computed at 0 comma 0. Okay, so that's the main aim, and then we can do the test for the point, whether it is maxima, minima, saddle point, etc. So let's first evaluate my del f by del x. You remember is 2x, and my del f by del y is 2y. So del 2f by del x2 is again differentiating with respect to x, the partial derivative of x. So this is 2x. So I'll differentiate with respect to x 2x, which is 2 into derivative of x, which is 1, which is 2. Alright. Similarly, del 2f by del x del y means I have the partial derivative with respect to y and I have to differentiate it with respect to x. So what is my partial derivative with respect to y? It is 2y, and I have to differentiate with respect to x, a 2y. Okay, and if I differentiate with respect to x, you know y will be treated as a constant, so this is a constant here, and that means this is derivative of a constant, which is 0. Similarly, del 2f by del x, this is also 2f, I'm sorry the notation went wrong here. Okay, del 2f by del y del x, this is just the opposite of it, which is derivative with respect to y of the partial derivative of x, which is 2x. Here you know that if you are differentiating with respect to y, x is a constant. Differentiation of a constant gives you a 0. And similarly, del 2f by del y square or del y2 is differentiate with respect to y, the partial derivative with respect to y, which is 2y, and this is just 2 into derivative of y, which is 2 into 1, which is 2. Okay, so these are my partials, so I'll just write have computed my second order partials here. So this is done. So now what I have to do here is I have to compose them into the Hessian matrix. So let me create HF here for this particular function. So my HF is 2 0 0 2. I have just substituted the values here. Okay, here you can see it now. So this is my Hessian matrix, and what you can see is if Hessian matrix at 0, 0 will also be this only, because there is no x and y in the Hessian matrix, so I can't substitute anything now. So the Hessian matrix at 0, 0 will be 2 0 0 2. Okay, so this is done. Now my last step is the test. So once I have done my Hessian matrix at the critical point, I'll do my test, and my test is I have to compute two things here. I first have to compute, in the test I have to compute determinant of Hessian matrix, and second I have to compute fx of x, which is simply your del 2f by del x del x. Okay, so I know already I have done the second part. I have already computed this. This is just this, okay, which is 2. So this is 2. And what is the determinant of Hessian matrix? The determinant of Hessian matrix here, if you will see, is 2 minus 0, which is also 2. So determinant, 4 minus 0, which is 4. Okay, 2 into 2 minus 0 into 0. This is what my determinant is, which is 4. Okay, now again the test points, the postulates of how after computing x, what is maxima, what is minima, and what is saddle point, we have already discussed. I'll quickly give you a recall. Once you compute these two things, if the determinant, so this is just a note which we have already discussed, if determinant of Hessian is greater than 0 and fx of x is also greater than 0, then it is the point of minima. If the determinant of Hessian is greater than 0 and fx of x is less than 0, this is maxima. If determinant of Hessian is less than 0, then this is directly a saddle point, which is neither maxima nor minima. Okay, neither max nor min. And if my determinant of Hessian is equal to 0, the test fails. Okay, so which condition has been satisfied by our function? You can easily see that our particular function satisfies the first condition, where determinant of Hessian is also greater than 0, which is 4. It is greater than 0, and the fx of x is also greater than 0, which is 2. Right? So that means what we conclude, the critical point, which is 0, 0, is a point of local minima for the function f, which is equal to x square plus y square. Okay, now this point might also be the global minima. We have not checked for global minima yet, because for that the test is different, but at least we have concluded that this will be a point of local minima. Alright, so this was your Hessian approach. For other functions, do the same thing. Your all steps are same. In the end, just check which condition is true. These are the conditions. Alright, so now what we can do is we will go to the mathematical computation tool called GeoGebra, and using GeoGebra we will tally whether our computations about the thing is correct or not. So what you can do is I'll open my browser, and this is my GeoGebra app. Okay, so what I can do here on GeoGebra is, let me just type the function here. The function is x square plus y square. Alright, so you got your function here. We will quickly see this function in a zoomed manner. This is your function x square plus y square. You can see it's like an ice cream cone. Okay, this function is very much like an ice cream cone, and you can easily see that this point 0, 0, I'll just see if I can open the pointer here. So yeah, this is my pointer. So you can, no, it's not selecting. Okay, alright, it's already selected. I can't get a cursor. So you can see easily that this point 0, 0 on this GeoGebra, okay, this point 0, 0 in this GeoGebra is my point of minima. This function is rising, and at 0, 0, this is the lowest point of this function, right? So this 0, 0 hence becomes my point of minima of this particular function. Alright, you can see it from this top angle as well, this bottom angle as well, that the function's minimum value is coming at 0, 0. I'll zoom it, you can see, and above 0, 0 it is just rising. So 0, 0 is a local minima, and hence you can also see over the entire range of the function, 0, 0 is the lowest point. So it is indeed a point of global minima as well, right? So this is what I wanted to explain to you, and I hope you have understood what I have tried to explain here. So this will help you further with the computations. Thank you.